why do we need to know the index laws? Why can't we just calculate things normally? For example, if we're given 3 squared times 3 cubed, why do we need to know that that's 3 to the power of 5? Why can't we just say 3 squared is 9 and 3 cubed is 27 and just work out 9 times 27? Well, with an example like this one, you don't really need index notation. And so far, those are the kinds of examples we've been working with, so I can see why you might wonder why we even bother. The truth is, index notation and the laws around it are actually a lot more useful when we don't know the exact value of the base or even the exponent that we're dealing with. For example, you might get asked to simplify an algebraic expression that contains index numbers, something like this one: x squared times 2x to the power of 6. Remember, a letter like x in an algebraic expression is just a code for an unknown number. This expression is like saying we have a number multiplied by itself times 2 times that same number multiplied by itself again 6 times. Now if we break this expression up, we'll have x squared times 2 times x to the power of 6. Notice that x squared and x to the power of 6 have the same base. It's an unknown number, yes, but it's still the same base, the same number, just unknown. So we can use the index law for multiplication. The index law for multiplication tells us we need to add the exponents. So we'll have 2 times x to the power of 2 plus 6, or 2x to the power of 8. These are not hard questions. The index laws still apply, so it's just a matter of choosing the right index law. Let's try a slightly harder question. Suppose we had x cubed times y squared over x times y cubed. So we're going to need the index law for division here. On the left we have x cubed divided by x. Now remember, x by itself means x to the power of 1. The index law for division tells us to subtract the exponents, so this will be x to the power of 3 minus 1 on the top. 3 minus 1 is 2, so we would get x squared on the top. On the right, we have y squared divided by y cubed. Now we could take 3 away from 2 and have a negative exponent on the top that we need to deal with, but remember how there's a faster way? If we want to avoid negative exponents, we can just move the 2 down and subtract it from the 3. Either way, we'll end up with y to the power of 1, or just y, on the bottom. So we'll have x squared over y. Again, we can expand this expression if you like, and show that there are 3 x's on the top, x times x times x, times y, over x times y times y times y. After crossing out all of the pairs we can find, we'll be left with x squared over y, just as we found earlier. Now notice that we can't do anything more with the x squared over y. X and y are both codes for unknown numbers, but they are different letters, which means that they code for different numbers. So we can't use the index law for division here, because the bases are not the same. Sometimes the exponents can be unknown as well. Again, don't panic, just follow the index laws to simplify the expression as best you can. For example, suppose you had 3 to the power of x, in brackets, to the power of y. We have an index number raised to a power and then raised to another power. So it looks like we can use the index law for powers here. The index law for powers tells us we need to multiply the exponents inside and outside of the brackets. So we would have 3 to the power of x times y. Done! As you can see, these are not that tricky once you get down to it. But you might be wondering, when would we even see algebraic expressions or equations with unknown numbers outside of these drills and worksheets? I'll try and give you a semi-realistic example. Suppose you're a biologist and you're growing a culture of bacteria for some kind of experiment. So you're in the lab and you've got some bacteria growing in a petri dish. Let's say you messed up your records and you have no idea what the rate of growth is for this sample of bacteria, or even how many you started with, but you do know that it's been sitting there for 2 hours. Let's say you take a look and there's 200 bacteria growing in there. They'd honestly probably be way more than 200, but I'm just choosing easy numbers for simplicity's sake. Anyway, so you leave the dish alone and you come back after 3 more hours, so now it's been 5 hours altogether. And now you take a look and there's 200,000 bacteria in the dish. Now, say you wanted to find out, for the purpose of your experiment, what is the rate of bacterial growth every hour? Well, we know that in 3 hours, the bacteria multiplied by 1,000, but we're looking for an hourly growth factor. 200 times blank times blank times blank equals 200,000. 3 blanks because of 3 hours. Instead of a blank, let's use a pronumeral, a letter. Let's say 200 times x times x times x equals 200,000. And now I have to find out what x is. X times x times x is x cubed, so our equation is 200 times x cubed equals 200,000. And we know that the total increase in bacteria over 3 hours was 1,000-fold, so from that we can conclude that x cubed has to be equal to 1,000. And if x cubed is equal to 1,000, then x will be the cube root of 1,000. Now if you like, you can pause the video now to work out yourself what the cube root of 1,000 is, or in other words, what x is. The cube root of 1,000 is 10. 10 times 10 times 10 equals 1,000. X equals 10, so the growth rate per hour for the bacteria in the Petri dish is 10. And from here, we can actually work out how many bacteria were present at the start. If there were 200 after 2 hours, and they've been multiplying steadily by 10 every hour, then we can work backwards. Originally, there must have been 200 divided by 10 divided by 10 equals 2 bacteria. Again, these are very, very fake examples. Bacteria don't multiply this slowly in real life, but I hope you get the gist. One of these days I'll make a unit on exponential functions where we'll go into these types of questions in a lot more depth, but for now we're just going to focus on simplifying expressions. In my next video I'll go through a few more worked examples with you guys, and then it's scientific notation and review, and that's it. I hope you all enjoyed this lesson. As usual, feel free to give me any questions or comments down below, and I'll see you next time at Sneezy Teaches. Bye!